I'm just going to start this by asking who knows what a relay is and how they work. Any hands? A couple of people, right. Who knows what a vacuum tube is and how they work? Right. And who knows how a transistor works and what they are? Good, quite a few people. Some people not, so it's going to be really quick so that the rest of the presentation works well. A relay, you put a little bit of current in here, the right amount. This goes down, closes those two contacts. And if you wire it right, when you turn it on, you can latch it. That's really important. Vacuum tube, have a bit of current flowing through the filament and a bit of thorium on there, and we get a cloud of electrons, and a high voltage draws them that direction, and a grid, because of its proximity and the size of the gaps, oh that's loud, can cause them to shut off and not go that way. It's just about using a small amount of, or small voltage to control a large voltage. And a transistor, put a bit of current in the base, flows down through the emitter on this one, and we can switch a voltage across the load. So those three elements are sort of, if you're happy with that, then we can move on. And by the way, I'm just taking a lot of my literature from two books. This one I was given when I was a kid. I was born then, but certainly my dad gave it to me well after that. And it's really cool because it's an Electronics Australia publication. The other one, 1960s publication, so that's where I'm trying to get most of my photographs from. Really important to recognise that the computer era was jump-started by the telegraphy industry. So switchgear and teleprinters and stuff, they were just like the perfect thing to apply to computing in the early days. Relay logic, uni-selectors, paper tape devices. And interestingly, 1936, the Creed teleprinter was used on the Harwell Witch Dekatron computer. So really good crossover there. So just imagine for a moment if we didn't have memory in the form of integrated circuits, how we would store information. That's what this is all about. The innovations and the struggles they had to actually get memory going. And we're going to go over ROM, RAM, not so much the mass storage, but crossover memories as well, where certain things like a hard drive was used as random access memory. And some of the things we're going to just touch on are microcode, program counter and other registers, because that is memory, configuration data, BIOS, boot code and the like. So the first thing is relay-based memory. We can store information by using two relays and energising them to set and clear the data. And uni-selectors, we can, by sending a number of pulses to the uni-selector, we can basically store that number on it. So it's just like a relay, except it's got a little ratchet that drags the wiper around. So Conrad Zuse in 41 completed his Z3 computer, and there's a spelling mistake. Could store 64 words using 1048 relays. And if you divide that by 64, you get 22 bits, which means there's one relay per memory cell. I couldn't work out how they did that. I think they used the latching mechanism in that previous slide to latch or inhibit whichever relays wanted a 1, they latched, and they inhibited with just a bank of load relays or something. Yeah, that's probably the earliest case of electrical memory device. Mind you, that 1905 adding machine out there, it's got 10 pounds, shillings, pence, halfpenny and the like. It's got 10 digits, so that's equivalent to 5 BCD bytes. You know, 2 bytes per thing, so there's 5 bytes of memory on that device, I guess. So vacuum tube flip-flops, or vacuum tubes can be configured as a flip-flop, and in the computing world we want a 1 or a 0, so it's off or on, not like a radio where we've got a fluctuating signal. By turning this one on, it inherently, through that resistor, forces this one off. So you can toggle, well, there are our drive lines there. So by using the set and reset pins, we can store one bit of information using a flip-flop. So that vacuum tube there has two elements, so we could make that circuit with one vacuum tube. And IBM, I stole that from Hackaday, so this is a replica of the IBM TR2 flip-flop unit. So one bit of information, not one byte. Transistors, same thing, they're either off or on. When I turn that one on, that one turns off. And with a bit of extra circuitry, we can load the data and force it to load that information, so you clock a 1 or a 0 into the circuit. So it's a set, reset, or a JK flip-flop. So again, that stores one bit of information. Charge transfer tubes and dekatrons. Absolutely incredible. The Dekatron was designed as a counter, and it automatically incremented when you pulsed the, what they call them, the pusher, and the one electrode pushes, one draws, and you can basically move a cloud of ionised gas from one spot to another with no additional electronics. So you can make a frequency counter by stringing a whole bunch of these together and just having a single transistor flip-flop at the start to drive these pulse lines. We can have a frequency counter, no other components, aside from a gate, so a pulse counter. But the Harwell Witch made use of dekatrons, so that's how a dekatron's supposed to work. You make a cloud of ionised gas and you push it from one electrode to the other. So the Harwell Witch, 1951, this thing here is actually, they've got it working at the Bletchley Computer Museum in the UK. And it's a really interesting machine because the dekatrons are not only used as a store for information, but it's also how they do arithmetic. So if I pulse a dekatron 10 times, it carries to the next one and stores the information as decade information, so they then translate that down into Bordeaux of all things, 5-bit Bordeaux, and push it out to a printer or a punch. So you can see in here, we've got a bunch of dekatrons down there, but there are relays and there are vacuum tubes as well, so it's a bit of a beast. So the Dekatron, for example, the paper tape reader and punch use dekatrons to buffer the information, and a bunch of vacuum tubes to actually read the information off that circuit. I haven't tried to reverse engineer that in my head, but you get the gist. The Dekatron is basically a storage element. So the Trocatron, what a great name. This is an Australian-made vacuum tube. It uses a vacuum in here instead of a partial pressure and no ionising gases. So now we've got a stream of electrons as the actual storage element. And by using these crazy arrangement of little grids and pushes, we can push the stream of electrons from one electrode to another. But more commonly called a magnetron beam switching tube. So Australians got Trocatron, but Burroughs went for MBS magnetron. So there's a magnet around it to ate it. The reason they did this is that because it's evacuated and it's got no ionising gas, this thing can run at 20 kilohertz instead of a couple of kilohertz. So at least 10 times faster. And then if you want to display the data, they put a Dekatron in front of it or a Nixie tube or whatever you like. So that's, and again, if you have an ionising or a beam of electrons and you put a bit of resistance in the plate, then you can take those out and read them off as data. So that's how they've turned a counting device into a data storage device. Am I going too fast? I'm trying to get through it because I've got a lot of really cool stuff. Good, thank you. So delay line memory, in essence, if you put information into a delay line and feed it back, and you can store more than one pulse inside that period of time, then you've got yourself a memory. So if I do that, that pulse travels through this piece of wood and comes out the other end here a short time later. I could turn this into a memory device if I put my mind to it. In fact, there are a lot of interesting materials they use to try and make delay line memories work better than the most common one, which was the Mercury Column. The struggles you've got is timing circuits embedding the clock into the data, degradation of the data, so you have to regenerate it, read-write logic timing, and understanding the delay medium to work out how much data you can put in it, and the data density. That was a real struggle. So with Mercury Column memory, they used a piezoelectric transducer, and it basically, when you put a sharp pulse on that, a pressure wave flies down the delay line, comes out, hits the piezo transducer, and the signal's detected with that, and then regenerated, and had the clock reloaded as well. A lot of people call them acoustic shockwave, but shockwave through mercury is at 1449 metres a second, not 330 metres a second. Oh.
How many bits you can store in.
Aha! We'll get to that very soon. EDSAC. EDSAC stands for Electronic Delay Line Storage Calculator, so the name is implicit in how that thing works. And that was 1949, and that's the EDSAC memory, and they have a multiple stack of delay lines, and that one there initially was loaded with 512 locations, 18 bits wide, but the thing didn't work terribly well, so they could only use 17 of the bits. It was real cutting edge at the time. So the UniVac 1 in 51 also used Mercury Column memory, and that is the UniVac 1 memory, and this little piece of electronics here looks ominously like the driver modules that the ACMS have got out on the table there. I would strongly suggest that I can't remember what one they claim it's from. I would suggest that that's being used on multiple computers. Sorry? CIRAC, that's right, yeah. So that could well be designed and built in the same lab as this one because it looks so similar. Now, a really interesting thing, patented in February 53, applied for in 47, was a patent for the delay line memory in the States. But look at this, Alan Turing in 52 applied for it in 51, so he was right in the middle of it. So not only was he a really clever guy, but he was a bit of an innovator as well in the form of hardware. So EDVAC, 128 mercury-filled tubes, 5 feet long, storing 384 bits of information. Now that's a lot of hardware for a couple of bits of info. That is crazy. The biggest problem is temperature. As the computer room heated up, the mercury expanded, and now you've got synchronizing problems, and the hardware struggled with it. So a hot computer room made unreliable computer memory. So at that time they started trying to come up with all sorts of things. They used glass rods and tried to use various solids like steel rods and stuff to try and get the thing reliable as well as high storage. So elasticity of the material as well as stable temperature coefficient made for a lot of research to try and get them to actually work reliably with high capacity. So we'll get back to some other delay lines in a tick, but we'll go on to Williams tubes. They are a crazy, crazy piece of technology. In essence, you have a... I don't know where I got this from. It may or may not be a Williams tube, but it could easily be. So it's a cathode ray tube oscilloscope. An electron beam is fired up here, and some little plates move it. Electrostatic plates move the beam in X and Y, and a Z-axis is basically controlling the intensity. So you can draw a dot or no dot. So the whole idea of a Williams tube is you draw a bunch of dots across the screen, and here's the really interesting bit. You don't need phosphor. The electron beam strikes the surface and creates electrostatic charge on the outside surface of the tube, and that's the information, not the phosphor. In fact, sometimes they put Williams tube in and then they put it with no phosphor, and then they put a second tube in so that you could see the data externally without interfering with the Williams tube. So there's a Williams tube, and it's all screened, and a front cover comes over with this plate which doesn't touch the tube. It has to stand off from the tube. So here's a bunch of little dots, and here's a bunch of larger dots. The small ones represent a 0 and the large ones represent a 1. So how, with a single plate, do you read all of that data? So one single plate reads all of it. And the answer is, if I put a 1 here, the sum of the static charges on the surface changes slightly. So they use a differentiator, high gain differentiator, to detect the change on that static plate. When I fire at one that's already a 1, no change happens. When I fire at one that's only got a small dot, this change happens. So it's recycled, the data fades away, so the recycle time is only a couple of milliseconds. So lots of electronics to make these things work. And to erase a bit's really odd. You either draw a big fuzzy dot or you draw a line through it and the charge dissipates. So they rely on, I don't know, it's crazy that it actually works at all. I've got to do more research, maybe turn that into one. So IBM 701 used the Williams tube in 1952, the Ferrite Mark I in 1953, with great success. They worked, but a lot of effort to get a small amount of memory. So that's the actual diagram for a Williams tube. You've got your deflector plates and your probably Z-axis control over here somewhere. Time base, amplifier to regenerate the data and reload it back in. That's a really rudimentary drawing. There's a lot of electronics to make these things work. And I've pretty much gone over that. So it's not a FIFO memory, but you have to regenerate the data. So onto something that's absolutely bizarre. The magnetostrictive not magnetorestrictive. It's magnetostriction, and it was discovered by James Joule in, I think, the 1800s. And I'm going to just draw what you see there. So there's a big piece of wire flying around, and the cross-sectional end of the wire has really thin, flat nickel straps spot welded to the top. This is about 0.6 of a millimetre, and it's got a set spot welded to the exact opposite side of the wire, and a coil here, and a coil here, and a biasing bar magnet, and it's hooked in antiphase, and basically all the magic happens not on the delay line, but inside there where the magnet and the coils are, and this is just a rubber mount to hold it securely while those nickel straps are spot welded onto the wire. And the magic is with a bit of bias, I'll just go with the Joule effect. Basically, when you apply a magnetic field to some ferromagnetic materials, they go eek and shrink. It's why transformers buzz. People think they buzz because the magnetic field is pushing the plates apart, but it's actually the plates vibrating because they're changing dimension. The Villari effect is when you stress a piece of ferromagnetic material, stretch it, it actually changes the magnetic field around it, creates a small magnetic field that can be detected. So by putting a pulse on here, we can cause this one to relax and this one to go tight, and the delay line goes beep, little torsional shock wave. So the actual delay line is a mechanical torsional shock wave that spirals down the wire and then pops out the other end, and the Villari effect causes a pulse to be detected by the receiver. So, yeah, pass that around.
Here's one I prepared earlier.
Now, 40-something years ago, I foolishly was a junior lab, 45 years ago I was a junior lab tech, and I was given that to throw away, and I ripped it apart and threw all the bits in the bin, and I thought, that is fascinating. There's a magnetostrictive delay line memory out of a Frieden Model 13 calculator from the 60s. So that's a really tiny one. Actually, I can pass that around. I've actually got this one running, just sending pulses through it to see if I can maybe hook up an Arduino and store data on it. So drum memory. Drum memory is typically thought of by people as a place where you store a file. But when you have a huge array of read-write heads, it can be mapped into addressable memory rather than a place to store stuff. So that one there is an IBM, and I think they actually nicknamed that the drum computer because it hinged all of its RAM on that thing there, so not storing files. Oddly, PDP-8i from I think the late 60s, they had a thing called an RFO8 or an RSO8, so a rotating file, but it had a single platter. It's nearly half an inch thick with a whole bunch of spiral permanently loaded heads, and they found that it was faster than the core memory in the PDP-8. So they actually wired up the electronics to use the hard drive to cache the memory. So in the modern era, we cache slow hard drives with fast memory. Well, they made their computer by doing the exact opposite because Ferrite core was so much slower than the RS8 monster hard drive, which didn't have much storage. So yeah, there are quite a few drum memories that had huge number of heads that were quite high performance. So Ferrite core memory. Does everyone here know how Ferrite core memory works? No, not too many hands up. Very quickly, if we've got a ferrite bead and you pass a current through a wire, if the current is high enough, you can cause a magnetic field to go this way with the current through there, I think. Yeah. But if I put a current that way, I can cause it to have a magnetic field going the opposite direction. So we've stored a 0 or a 1. So the trick is to have 2 wires, because we've got to address a whole bunch of memory, and we make neither of these enough to magnetise the core, but the sum of the 2 enough to magnetise it. That means that we can energise the X row and the Y row and select one of 16,000 ferrite beads on a panel like that one there, and magnetise it one way or the other. The interesting thing is that to detect, we have another wire going through the ferrite, and if you magnetise this way and it's currently magnetised the opposite direction, when you send that right pulse to it, in opposition, you get a tiny little magnetic current through this wire here, because this thing here objected to being magnetised the other direction. I'll say it that way. So now we've got a way of reading and a way of writing, but if I write a 1 to detect if it was a 1, I've destroyed the data, which means that every time you read, you've destroyed the data, so you have to write it back. So it's destructive read memory. So to make it read-write memory, you have to have a bit of trickery to... If you wrote a 0 and it was already a 0, the computer goes, well, it was already a 0, I don't have to do anything about it. So anyway, that's pretty cool. So I'll just pass this around. When I was a kid in Fiji, 30, 40, a long time ago, I found this in a dumpster at the Ports Authority in Fiji, and that is a Potter Instruments key data recorder with a ferrite core memory storage on it. I was a bit addicted. Yeah, I found it in a dumpster. It's true. That's one, I can't remember where it's from. I think I bought it at a junk shop somewhere. So there we go. Now, the GE225 that I've been talking about out there, it used what's called 3D core memory. This is out of a controlled data, I think. You can pass it around. So what they do is they make a plane of ferrite beads and then they stack them, but they wire another wire into the bead that loops through all of the beads on that plane, and that's called the inhibit. So what it does is it just biases one of these lines. It puts a current bias on the sum of the currents through the bead, so that that one plus that one minus that one equals not enough to change the magnetic field in the coil, in the ferrite, so it can't be read. And then they stack them and have separate inhibit lines for each layer to give you a 3D memory. So that's a 2D memory device there. And I've talked about how you access them. And that's a 3D core. So there's an extra wire in there. Yeah, well, that's unneeded. And yeah, so I've already talked about that. So there's our sense and inhibit and our X and Y lines to give us stacked memory for extra density. Now, Twistor memory came in and then it went out really quickly because integrated circuits popped into existence. The idea of Twistor memory is to make your wire array and then drop little drops of ferromagnetic material down onto it, so blobs rather than feeding them through beads, which means it could be made in a production line rather than have people there with magnifying glasses lacing thousands of beads, which is what made them so expensive. Thankfully, they didn't last long. Now, read-only memory. My goodness, there are some crazy things out there. First thing is a diode array where you can just put pins in and there's a little diode inside here. I could write a boot code by just placing pins in here and boot a PDP-8 using one of them. Or I could have a little motor drive and a bunch of inserts in here and write a program on a mechanical device to boot a computer. So yeah, read-only memory, programmable, that's a PROM. That's PROM as well, I guess. Diode Array boot board. So here's the boot ROM out of my PDP-8. I'm not too worried about the static.
You can read the code.
So by putting a bunch of diodes on a row, each row is one of the memory addresses. Where there's a diode, there's a 1. Where there's no diode, there's a 0. So code 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0. So, yeah.
The old computer space arcade machines, the first commercial arcade machines, used diode ROM to have the shapes of the rocket ship and the flying saucer, and they were laid out on the PCB in the shape.
To look like a rocket ship.
Yeah.
Now you're talking. I like that. I used to fix arcade games with pocket money. All right, so that's the PDP-8 boot board. So there's enough code there to load the start address, hit the go button, and then it loads the OS off the reel-to-reel deck tape or the RLO1 like the one out by that PDP-11 or others. So, tape loop. This is the dual tape loop from the Colossus computer at the Bletchley Computer Museum. So what they do is they load the tape on this crazy loop, and the tape is basically the unencrypted data from scraped from the receivers using things called undulators, and then translated into punch tape. And then they splice them together and put a start marker on it, and then this tape whizzes through it at astronomical speed. It's like, I can't believe they actually did it, it's so fast. The idea is that the data flies through it so quickly that the read registers, basically if you want byte 5, it's going to fly past any microsecond now because it is actually flying at a high speed. I don't have the data in my head about how fast and how many bytes, but the point is by whizzing the data through like that, you've got read-only memory in the form of the data they're processing to crack the German codes. Another form of read-only memory, this board is out of the HP 9100 on that row. I've spent a fair bit of time refurbishing that machine, getting it going. So that's the prototype rope memory out of the Apollo guidance computer, and that's what a ferrite bead looks like with a huge number of wires flying through the ferrites. So that's not from that one, that's from a different, that might be from the real Apollo guidance computer. Anyway, moving on. So how does it work? In essence, we have 4 beads for 4 bits of data. No, 4 addresses. In essence, if we put a pulse on wire 3, nothing's detected here because it didn't go through the bead. Nothing's detected here. Something's detected here, so we'll call that bit a 1. Nothing detected here, so we'll call it that bit. Yeah, so that's 0, 0, 1, 0. And by scrolling through these lines, depending on how the wire is woven through the ferrite beads or not, we've stored data. So if you get the code wrong, you're in a whole world of trouble. So this is the back plane out of the HP 9100 down on that row. I should have the guy's name. There's a guy who restored one, and he's got like 20 episodes on YouTube of his restoration and described how this thing worked, because I didn't know at the time, and it's astonishing. Behind that panel are 8 Teflon double-sided circuit boards with tracks and vias, nothing else. So how do you store data with tracks and vias and no other electronics aside from differential amplifiers to detect, a diode array to switch, and pulse generators to send a pulse through the address lines? And the answer is amazingly simple, except crunching it down into a small space and making it with the absolute certainty that you are not going to get it wrong. 16 layers on Teflon double-sided boards in the 60s. In essence, if I put a pulse on, so this isn't a binary, this is, you select that, so it's demultiplexed. Selecting this line, I put a pulse on it, and this piece of track here is parallel to that, generates a current going that way, and over here it generates a current that way. So it's induced a current. This piece of wire is basically a loop. There actually should be a resistor here. So I've generated a voltage across this differential amplifier because it's going this way. That pulses positive. And over here, it's going the other way. So this one pulses negative. So going on, this is 1011. 0, 1, 0, 0. I got that wrong. So 1, 0, 1, 1, 0, 1, 1, 0, and so forth. So in essence, they shrunk that down onto, did I? Right. Yeah, so that board there, this segment here, it's about that size, with 16 layers, offered them 1.8 kilobits. That's 64 29-bit words of read-only memory that you can never change except by making a fresh assembly. So you better get it right. So yeah, I tried to talk fast because I could ramble on about these a whole lot more because they're so fascinating. Any questions?
The Usagi drum memory is from a Bendix G50.
Yeah.
A YouTuber called Usagi Electric.
Yeah.
He has a Bendix G15 which has a drum memory. It goes into that.
All right.
Where he has to.
So that's one that uses a lot of relays as well, I think.
Yeah, tubes.
That's a tube.
Tubes. Yeah. Yeah.
Oh, very good.
Quite interesting. Yeah.
All right. Well, I hope you found that fascinating. I certainly do. It's just bizarre what the effort required to get some memory. Thank you very much. You're welcome.
Did your technology stop at a certain age? Or a certain
No. In essence, all of these, there's some overlap in those technologies, but Ferrite went straight to ICs, and Ferrite trumps everything there. Yep. Williams tubes, magnetostrictive, memory delay lines, the whole lot. They're totally trumped by Ferrite core memory. And as soon as we got out of... Okay, so Ferrite core, just by the way, rope memory didn't last long, so Ferrite core was so reliable that writing to it and then locking out, inhibiting the layer so that it's essentially a ROM, meant it's a PROM that can't be damaged by the user. So Ferrite core really went right through to ICs, and in fact there was a huge overlap in the DEC computers where Ferrite and MOS memory were both available and running on the same computer even. Bubble memory was around, it came around after IC, so I left that alone, but it didn't last long, thankfully. I hope you liked all of that. Thanks.
This was recorded at the Canberra Vintage Computer Exhibition 2024. To find out more, check out the links in the description.